Hello, everyone. In the past few videos, we've been introducing parametric curves, and in particular, we've been focusing on doing our usual calculus on these things. So taking derivatives and maybe finding the arc length of them as we did in the previous video. Now we're going to continue that discussion in this brief video, and we're going to show how you can find the surface area of a curve or of an object that is rotated around either the X or the Y axis. So let me give you some formulas. We'll use an example, and that will be what we'll talk about in this brief video. So here's the basic idea. If we have a area or a surface of revolution in the plane, we would like to compute the surface area. So how do we compute that? Well, here I'll give you a formula, and then we'll talk about it. So area of surface of revolution in the plane. So maybe the best thing to start with is to pause this video and go back to when we did this at the beginning of the course and see if you can guess or if you can infer what that formula is going to be. If you remember correctly, there is a ds computation, the length of the curve, that is being rotated around one of these axes. So we're going to see where that thing comes in just a moment. But let's first set the scene. So let's say if a smooth curve, let's say x is equal to f of t and y is equal to g of t. So this is our usual parametric curve definition with t running between a and b. If this thing is traversed exactly once, so we don't want to go around and around and around in a circle here. So it's traversed exactly once as t increases from A to B, then the area of the surface, or then the area of the surface generated by revolving the curve around the coordinate axes, around the coordinate axes are as follows. So I'm going to do it for each of the coordinate axes individually. And we're just going to do this for the y-axis and the x-axis. You can infer how to change this around if you'd like, based on what we did in the previous video on this, if you want to revolve around, say, x is equal to 1 or something like that. So 1, about the x-axis. So about the x-axis, and we're going to make the assumption, that y is greater than or equal to 0 here. Then the surface area S is given by the definite integral from a to b of 2 pi y, and then times this integral, this square root. So dx dt squared plus dy dt squared dt. Maybe that square root's not my best. I'll extend it down a little bit so we can see it a little better. But the 2 pi, that should be familiar where this thing is coming from. This is the circumference computation. The y, again, this is the radius. And then the square root term, that's your ds term, your arc length differential, right? So again, you might want to compare that to what we did in the previous video with arc length, and then cross-reference that with the first video that we did on these surfaces, these areas of surfaces of revolution. And then similarly, if we go about the y-axis with x greater than or equal to 0, you basically get exactly the same thing. You're just going to switch the role of x and y. So you get 2 pi x, and then this huge square root. Again, this should look familiar. This is sort of a Pythagorean identity. you're looking at the change in the y direction, the change in the x direction, and then the change in the direction of the vector that goes, has coordinates dx dt and dy dt. So this is your sort of general formula, right? This is the natural extension of parametric curves. Let's just do an example. Let's see it in practice, right? We have a nice formula in this case. Let's put it to use. Let's play with it a little bit and see how it works. Let's consider the circle centered at radius 1. So consider the circle of radius 1, let's say, centered at 1, 0. Sorry, let's do 0, 1. At 0, 1. And it's going to be parameterized by, this is a fairly standard parameterization, cos of t, and then y is equal to 1 plus sine of t. So that center at 0, 1, that's just coming from shifting y up. And we're going to let t run between 0 and 2 pi. And then use this to, let's say, find the area of the surface swept out by revolving the circle about the x-axis. Okay, so I'll spare you a drawing. The nice thing here is now we kind of just have a really nice a nice formula that we can plug this into. In our case, y is greater than or equal to 0, so we can use that number 1 formula here. We essentially just need to plug in some values. So first things first, dx dt. Remember, we talked about how to do this in a previous video. This is just a standard derivative. This is the derivative of cos. We get minus sine of t. Similarly, dy dt. This is the derivative of 1 plus sine of t. Just gives us a nice cos of t. And so this tells us that our surface area is equal to integrating from 0 to 2 pi. That's our a and b bounds. 2 pi, and then times y. So I'll just write out the formula so we all have it since I changed pages. dy dt squared dt. And the really beautiful part of these parameterized curves is that everything ends up in terms of t, right? So it's a fairly simple problem where we don't have to worry about keeping track of, are we integrating with respect to x? Are we integrating with respect to y? Do I have to convert everything back and forth? Right, this hidden variable underneath t, this parameter, allows us to sort of simplify a lot of the computations that we've seen. Okay, so we get 2 pi, and then 1 plus sine of t, that's the integral, or sorry, that's the y along this curve. And then in here, we have minus sine of t squared plus cos of t squared. Wow, I wonder where we've seen that before, right? This seems to come up quite a bit. This is the usual Pythagorean identity. Maybe let's put it in green. That tells us that this whole thing under the square root is equal to 1, because when you square the minus sign, it just becomes sine squared. And now this is really just the integral of 2 pi of 1 plus sine of t dt. Maybe we'll put some brackets around that just to be careful. And so this gives us 2 pi and then t minus cos of t, running from 0 to 2 pi. The periodicity on cos of t in this case is going to mean that this thing, its integral over one period is equal to 0. It spends just as much time above the x-axis as below it. And so we get a surface area of this torus shape, right? The circle swept around the axis. It's going to be 4 pi squared. So it was a short one, but it was a nice one, right? It showed us how to simplify some things that probably gave us a headache at the beginning of this course because they were relatively complicated. Now we can see with parameterized curves that things sort of get simpler. And we saw this in the previous example or in the previous video as well with arc length.